So in this short video I will be going over Marine Science section 4, 4.4, which is population and sampling techniques, and I'll go over the math and the fieldworks in the section called Measuring Marine Biodiversity. I do apologize for my voice, I'm a little struck by COVID right now. So often the thing we are struggling with in marine science is to figure out how many are there of a given organism. And for some organisms it's easy. For example, blue mussels and oysters and so on, you can just go out and count. But for more mobile creatures we need a different way of doing it, and that is why we'll be looking at the Mark-release-recapture technique. For some organisms this is quite simple. Snails who just move around on a beach, you can just label their shells with a non-toxic label. But if you're doing this with sharks or whales, it does of course require a much different way of doing it, and this is a whole discipline in marine science, how to label and then mark, release, recapture different animals.
So when we in marine science need to calculate the biodiversity of mobile species, just counting them is hard because they move around. And in that case we will have to use the Mark-release-recapture. And to do that we use a Lincon Index. And the Lincon Index uses a following formula, that n equals n1 times n2 divided by m2, where this n is the estimated population size, n1 here is the number of species, individuals we capture in the first sample, n2 here are the number of individuals captured in a second sample who are both marked and unmarked, and m2 here is the number of marked individuals recaptured in the second sample. To do so, we have some assumptions. We assume the marked individuals are unaffected by the tagging process. We also assume the marked individuals disperse to the unmarked population. We assume that all animals have the same probability of being marked. We assume that markings are not lost over time, that the second sample is random. We also think the effect of immigration, mortality and recruitment are negligible in this experiment. So let's have a look at a calculated example. Let's say that the first time we do an experiment here, we capture 120 of the species we'll look at here. And the second time, and then we mark those 120, and the second time, N2, we then find 200, but out of those 200, only 40 were marked. Then we have our number here to calculate our estimated population size. So our estimated population size would be n equals our first sample here, so n1 is 120, n2 is 200, and then we divide them by the 40 of the recaptured who were marked, and this gives us a n of 600. So the estimated population size here would be 600.
So when we want to figure out how many organisms there are in an area, we have different ways of doing it scientifically. And our goal is, of course, to be able to make our observations as accurate as possible. So we need some standards to go by. One here is a frame quadrant, as we see in the picture. The frame quadrant is a piece of plastic or metal that has a defined size, which we'll keep using. And what we do is that we place this somewhere at the sea bottom or on the beach, and then we look at what organisms are within that quadrant. And the reason for doing this is so I don't just look for the things I find interesting, but that you sample and record the things that are within a certain limit. Another way of sampling, which is also used a lot in terrestrial biology, is making a transect. And by making a transect, we make an area, which we then make a boundary for, and then we can look inside that area. In biology, also in terrestrial biology, we often use the method of making a transect. A transect is an area marked by a rope or anything else, so we can clearly mark what is inside the area and what is outside the sampling area. And one advantage is that a transect like this we can revisit several times a year, or we might revisit it a few years later to see the change in population size and what species we'll find within it. So using transects is a hugely important discipline in all kinds of biology. So a quick way of doing samples is having a line transect. In a line transect, the transect is placed in a straight line between 2 points in the direction of the environmental gradient we wish to study. For example, high tide or low tide, or reef boundaries in the coral reef. So there's two ways of doing it. In continuous sampling, any species that touch the line will be recorded. Or if we don't have time for that, we can use systematic sampling, when we then only record the species that touch the line within intervals, for example, for each 50 centimeters or so on. This can give us a quick look on the distribution of species in the area. Using a belt transect gives us a higher resolution than using a line transect. By using a belt, we take an area and then record what's within that. The belt transect method is an example of systematic sampling, so we can really go in and have a look at what species we'll find within it. And it also gives us, as you see here on the picture, a picture of how the different biotic and abiotic factors in the sample quadrant will affect the species distribution. A frame quadrant can also be used for random sampling. And there are several ways of doing this. The most basic random sampling is if you have a quite uniform area, let's say a seagrass meadow, we just place 1 or 2 quadrants within it and see what species we find. A more rigorous method is to generate a number of squares and then use a computer program or math to calculate what squares to sample. Both of these methods are used when we want to look at finding what organisms live in a certain area.